Hi everyone, welcome to the SAP2000 course. In this lesson, we will build a cantilever beam model, assign an I section, apply 3 load types, uniform distributed load, a tip point load P, and a linearly varying load. Then review bending moment, shear, and deflection. We'll also compare results against hand formulas. We'll learn how to show values, export reports, and adjust colors. Let's start a new file. File, new model. Set the units to n millimeter. We'll use a simple grid for the cantilever beam. Set the grid count to x equal to 2, y equal to 1, z equal to 1. And the total length to 100 millimeter in x. Leave y and z spacings as default and click OK. Turn off the 3D view for now. On XZ plane, you will see the grid. We will draw a 6-meter beam. Since the grid spacing is already set, just clear the left grid point and then the right grid point. Press Escape. The cantilever line is created. Next, we will assign boundary condition at both ends. Click the left end. Set it to fixed using quick restraints. Fixed. For the right end, set it free. Select the right joint. Joint restraint. No restraint. That completes the cantilever support setup. Now define materials and sections. Define materials. Add new materials. STA36. OK. Then define the frame section. Define section properties. Frame sections. Add an I sections. And name it. Confirm that the section dimensions are 200 times 200 with 8 mm web thickness and 12 mm flange thickness. Material, choose A36. Click OK to save the section. select the bin, then assign the section, assign frame sections, pick H 200 times 200. OK. You should now see the I section assigned to the align element. Next, define load patterns. Define load patterns. Add 3 patterns: uniform load, tip point load, linearly load. All 3 of our loads are live loads. For the first, uniformly distributed load. We will set the UD load type to live. Add new load pattern. Next, for the point load, we will set point type to live. Add the new load pattern. Next, for the linear load, we'll also set the type to live. The 3 load patterns have been defined. Click OK. Next, we will apply loads to the cantilever beam. Click on the cantilever beam. Assign frame loads. First, we'll apply a uniform load. For the distributed load pattern, we'll select a uniform load. For the system, we'll select global. For the load direction, we'll set the Z direction to positive. In the options section, we set add to existing loads. For the load section, we set it to -20. Then we will apply it. You will see that the -20 has already been applied to the cantilever beam. Click OK. Next, we will assign the end force on the right side of the cantilever beam. Select this component as well. Assign frame loads. For the end force, use point load. For load pattern, select point. The rest of the options are the same as before. For options, select add to existing loads. Where should we assign the point load? We are going to assign this to the endpoint. This is the relative distance, proportionally distributed across the entire member. 0 is the far left, 1 is the far right. And in between are 0.25 and 0.75. They are built in. We will only use 2 of them this time, 0 and 1. In the second column, we'll change it to 1. And for the load, we'll set it to -10 thousandths. The third and the fourth columns are both set to 0. Click OK. Next, we'll add a linear load. Again, select the cantilever beam. Assign frame loads. Distribute. Load pattern we choose linear. The rest of the options are the same as before. Uniform loads, set it to 0. How do we set the linear load? The leftmost point is 0, so load is 0. And then it goes up linearly to the free end, which is negative 30. So we set the second point to 1, which is negative 30. It will be like a linearly increasing load from the relative distance of the components 0 to 1, and then slowly increase to negative 30. Select 0 for the rest of the points. Then click Apply. You will see the load from the fixed end of the cantilever beam is 0, and the load from the free end to negative 30 is a triangular distribution. Click OK. Next, we need to run the analysis. This is a shortcut key here called Run Analysis. Click it and then Run Now. It will ask us to save it as, and we will save it as lesson 2. Next, we'll look at its bending moment diagram, shear force diagram, and the displacement. We'll select this member again. Display, shear forces and strains, frames, cables, tendons. In the case cable section, first select uniformly distribution load. The shear force diagram will display as follows. The cantilever beam has the greatest force at the fixed end and the smallest force at the free end. Next, we'll look at the bending moment diagram. Again, the cantilever beam has the largest moment at the fixed end and the smallest moment at the free end. Here, you can also see the bending moment and the shear force caused by the point load. We can see the shear force diagram is always minus 1030, minus 10 thousandths. The bending moment diagram is also the largest at the fixed end and the smallest at the free end. Similarly, the bending moment and the shear force of the linear load can also be seen. Click Apply to see the impact of these forces on the component. We can also see the output value here. In the options for diagram section, click Show Values and click Apply. It will show the maximum value. Let's adjust the units to make it easier to see. Here it is minus 90. The maximum shear force is minus 90 kilonewton. Next, let's verify that the data generated by SAP2000 matches our manual calculations. Let's first look at the UDL deflection. The quickest and the most direct way is to click Show Deformed Shape. UDL. Click OK. Click your mouse here, and you will see U3. It's 354 millimeter. Next, compare the hand calculation of the end deflection. The formula for the deflection is here. The parameter setting are W is equal to 20, L is equal to 1600, and the Young's modulus is 200,000. The hand calculation of I is 4.61 times 10 to 7 millimeter. So our calculation is 352 millimeter. The actual SAP2000 result is 354 millimeter. Why is there the slight discrepancy with SAP2000? It's about 0 to 1%. SAP2000's I value is more accuracy and includes fillets and chambers. SAP2000 also takes into account shear deformation. The parameter values and the model details are slightly different, so a 0 to 1% discrepancy is acceptable. This verifies that the model is consistent with our manual calculation and there are no errors. Next, let's look at the explore section. Let's look at the bending moment diagram for the uniformly distributed load. We also select this component. Display. And follow the same process as before. Select show values and adjust it to kmm. You will see the output section is 360 kmm. Okay, now we are ready to explore this diagram. You can actually adjust the color of this diagram. The color adjustment is down in options. Colors, output. Diagram field is the color of the positive and the negative values of the shape. All the color adjusted by other options. This is a negative value, so we can adjust it to bright yellow. It will turn this part bright. This will turn this part bright yellow. Next, we'll export the model, drawings, and the analysis results. First, click File, Export. We'll export the SAP2000 S2K file. These files can be imported later. This will be the model. Select, export all, and click OK. Set the file name to lesson 2, then click OK. You can also export the entire image. We'll resize it to make it larger. Then go to File, Capture Picture, curving window without the title bar. Set the file name to lesson 2. Next, we can output its analysis data. Similarly, go to File, Print Tables. To output the model creation method and its analysis results. The file name is result. This is the end of this course. The full file is on Gumroad in the description column. If you want to watch the continuous beam course, remember to subscribe, share, and turn on the bell.